Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 45, part A, and we are continuing our discussion of bivariate transformations. This is part 5. So far we've gone over several examples of the bivariate transformation theorem, using the bivariate transformation theorem for one-to-one functions. We've discussed the Cauchy distribution and the beta distribution. We found that there are results where we end up with the function of two random variables ends up being a beta distribution, and another case where the function of two random variables ends up being a Cauchy distribution. So we are going to continue with another example of continuous random variables, and we're going to start with the continuous uniform. So this is continuous. So the continuous uniform, not the discrete uniform. And we want to find the PDF when x and y are both uniform from 0 to 1. We want to find the PDF of x plus y. In this case, we need to let v equal x minus y. Okay? So rather than have you fumble around trying to find this v, we will use the difference. And so we have the sum of two uniform distributions and the difference of two uniform distributions that are the same. Remember that f of x is going to be 1. If we draw this, and we have 0 here and 1 here, and we'll have f of x here, then the area under the curve here, which is a rectangle, that has to equal 1. And this is a 1. So f of x was equal to 1 over b minus a. Here, b is 1 and a is 0, so we have 1 over 1, which is 1. And remember that y is identical, so y is going to be 1 as well. F of y will be 1 as well. And so x is between 0 and 1, y is between 0 and 1. We have a rectangular joint. If we look at the joint range of x and y, we have a rectangular space. Okay? So f of xy is, since they're independent, is just f of x, the marginal of x, times the marginal of y, which are both 1, so I end up with 1, and I end up with the joint range of x and y as x between 0 and 1, y between 0 and 1, again, this rectangle that I've shaded down here. Now, we've already said we've been told that we want x to be u minus y, or I'm sorry, u equals x plus y. I solve for x, I get u minus y. And if I solve for y in the other expression, which was x minus y, so I get x minus v. Okay? So I have u minus y, and then I can substitute in for y, which is x minus v. Make sure you keep your minus sign straight because it will completely mess you up if you don't. So when I distribute that, x becomes negative and v becomes positive. So I have u plus v minus x. So now I have this relationship where I have it defined in terms of x. So x is in terms of x. So x equals u plus v minus x. I'm going to add x to both sides, and I end up with 2x is equal to u plus v. Divide both sides by 2, I end up with x equals u plus v over 2. I do the same thing for y. I substitute in for x, and I know that x is u plus v over 2. So now I have u plus v over 2 minus v, so that'd be 2v over u minus 2v over 2. And I end up with y is equal to u minus v over 2. This is h2, this is h1. My Jacobian is the partial of h1 with respect to u, and that's going to give me 1/2. I take the partial of x of h1 with respect to v, I get 1/2. I take the partial of h2 with respect to u, I'm going to get 1/2. But when I take the partial of h2 with respect to v, I get negative 1/2. So again, I'm going to find the determinant, which is of this matrix, which is the Jacobian. So I multiply or take the product of those two elements in that diagonal minus the product of these two elements in the other diagonal, and I end up with negative 1/4 minus negative 1/4, which is negative 1/2. So the absolute value of j is simply positive 1/2. To use the transformation theorem, remember that g of u v is equal to f of h1 h2 times the absolute value of the Jacobian. But f of x, y was simply 1. There is no x or y in there. So this becomes a 1, and then the absolute value of j, the Jacobian, was 1/2, so that just gives me 1/2. And now I have to find the joint range of u and v. So I'm going to start off with x and y. So I have x between 0 and 1, y between 0 and 1, and I can substitute in for x. It's inverse transformation. So u plus v over 2. And so I end up with u plus v between 0 and 2. And I also end up with, substituting in for y, I end up with u minus v over 2. I multiply by 2 on all three portions of both of these, and I end up with u plus v between 0 and 2, and u minus v between 0 and 2. And so I'm going to break this up and look at the individual inequalities. So the first thing I'm going to do is I'm going to say 0 is less than u plus v. Whoops. And so I can solve this for v, and this would be that v is greater than negative u. So the line I'm going to look at is v equals negative u. That's the line for this. And I could say that u equals negative v. These are the same, right? Just which one are you solving for, u or for v? And then I'm going to look at this portion of the inequality, and that's going to give me u plus v is less than 2. I can solve for v. V is less than 2 minus u. So the line would be v equals 2 minus u. And then I could also solve for u. So u would be less than 2 minus v. And here I would have the line u equals 2 minus v. So I've got, so far I've got two different equations, two different ways to write each one of them. Okay. And so, so actually I want the equal to is what I'm going to look at. Equals to, that's the lines. And then I'll use the inequality to determine where I shade in the joint PDF. Now I'm going to do the same thing with this. I'm going to look at this portion of the inequality. And if I solve for v, I have that v is less than u, or u is greater than v. So I need the line u equals v. So that's one of the lines I need. And then I look at the other portion of the inequality. I'm going to look at u minus v is less than 2. I can solve that for v, and so that would be v is greater than u minus 2. So the line is going to be v equals u minus 2. Okay. So I have those lines, and I could solve it for u as well. So now I have taken each of the 4 lines that I end up with, and I have, so instead of a less than, I say equal to. I don't know why I put a less than there, just make it equal to. So this can be rewritten as u equals v. This could be u equals 2 plus v, or v equals u minus 2. This line is v equals 2 minus u, or u equals 2 minus v. And of course I have v equals negative u or u equals negative v, depending on which way I'm integrating. So This is very important. Now, when I look at this, if I'm integrating in x, then I have to break this up into two portions because I have this line here is the boundary to the left if I'm integrating in x when, in u when v is between 0 and 1. And then if if v is less than 0 or between 0 and -1, then this line is my first encounter. That's what I first encounter. And this is the second line. So depending on whether I'm above or below the u-axis, that determines whether or not I'm using this line and this line as my limits, or whether I'm using this line and this line as my limits in the u direction. Now, if I'm integrating in the v direction, then if I need to split this at 1, where u is equal to 1, when u is between 0 and 1, I'm going between this line and this line. And when u is between 1 and 2, then I'm going to integrate in v between these two lines. Okay? So now I can write this in terms of, I've said independent, and that's one of the ways that we say that we're writing u independently. I need to put that back and just get rid of this. Okay. So we're going to write u independent. U and v are not independent. There is no, this is not a square, this is a diamond. So u is not independent of v. But I can write it in terms of u. So I'm going to break up. So if I'm integrating, another way to say is if I'm integrating in v, then I'm going to break this up into two parts based on u. U is between 0 and 1, and then v will be between negative u and positive u. So, so between 0 and 1 for u here, then v is going to be between this line, which is negative u, and this line, which is u. Okay? And so that's what we have here. And between 1 and 2, for u between 1 and 2, then we're going between this line, which is v equals u minus 2, and this line, which can be written as v equals 2 minus u. So u minus 2 to 2 minus u. And then if we want to write this in terms of like we're integrating in u, then we would get this expression. So u would be between negative v and 2 plus v when v is between negative 1 and 0. And then u will be between v and 2 minus v when v is between 0 and 1. So I'll let you look at the picture and get comfortable with that is what's happening. And this is very important skill because you will need this on the homework and on the test. Okay. So the joint PDF of u and v is given as 1/2 if u and v are in B. I'll call that B. And actually I'm going to make these B's because that's what we've been using so far. So let's be consistent. The range of u and v. And 0 otherwise. Now I want to find the marginal of u. Okay. Now since I'm breaking this up into two portions, I'm going to integrate to get the marginal of u. I integrate across v. So I need to, it's important that I write both of these expressions for b so that I can easily integrate. So if I'm integrating across v, then I'm going to use this portion and this portion. These are my limits of integration depending on which portion of u. So, and that's what I've done here. So even though what's being integrated is the same, the limits are different. And so when I integrate this, I get u for u between 0 and 1, and 2 minus u when u is between 1 and 2. And so this is g of u. I could write that as v equals g of u, and if I do that, then I can plot this between 0 and 1 for u, then that is equal to, v is equal to u. That's this line here. And when u is between 1 and 2, then I get 2 minus u. V equals 2 minus u here. And so I have a triangular distribution that has its base on the u-axis. Now we find the marginal of v, so we integrate across u, and again using these limits of integration that we found when we wrote our joint range of u and v. So different depending on these two portions. And so if you look at this picture, this graph, you will easily be able to see which lines are going between, but it's easier for me to write it, to take away all the confusion and write it, where did it go? Where's B? Here it is. To write it in this two different versions here, so I can easily pick up that when I'm integrating with respect to, let's see, u, then I have u is between here, these two values and between these two values, depending on the value of v. Okay. So when I do this, when I integrate to find over across u to find the marginal of v, I end up with 1 plus v and 1 minus v. So again, I could say that u equals g of v if I want to. And this, then I have these two lines, if I'm doing it in the uv plane. And so that triangle is my distribution for v, my marginal distribution of v. And so that is a triangular distribution, but with the base on the v-axis, okay, between -1 and +1. All right, so that is this example. That's our last example of the continuous distribution. Please make sure you understand all of the examples we've done and that you can repeat them yourself, because it may not be on the homework, but it may be on the test that you have to use these techniques. So these are things that you want to have handy. Please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, come to virtual office hours. If you can't make it to virtual office hours before you need an answer, take a picture of your problem and a picture of your work so far. Email that to me, and I should be able to help you through email a lot faster and more efficiently. Please take care of yourself. We certainly hope to see you next time.